Hi everyone, welcome to the next lecture on special chapters of higher mathematics. Here we consider mathematical models of matrix games, also known as multi-person decision theory. We consider matrix game with zero sum, and in this same video we'll consider also a solution how to solve a matrix game in so-called pure strategies. In the next lecture, in the next video, because I'm splitting this video into halves, we'll consider matrix game solution in so-called mixed strategies. So the game theory, or we considering basically only the elements of games theory. The theory develops tools, methods, and language that allow us a coherent analysis of the decision-making processes when there are more than one decision maker, and each player's payoff possibly depends on the actions taken by the other players. In previous decision-making procedures, when we played with nature didn't play on purpose against us. For example, we played with nature. There were situations when the first party is to make a decision, and the other party, the nature, doesn't take the deliberate action to oppose their decision in response. For example, you consider bringing an umbrella with you, and you weighing up the odds of if there will be a rain or there will be no rain. So, the nature doesn't take deliberate action, like it just turns to be rain or no rain. But if we push this logic up to the next level and assume that nature starts playing against you, like every time you leave your umbrella home, then the nature will turn up a shower on you to reduce your payoff and to make you wet. So, and then we replace the nature with a second player who plays deliberately against you. Like in the game or when you make a decision, you want to maximize the outcome, maximize your profit, which is called the payoff. And your opponent plays against you to reduce your payoff. And we consider different situations. All the decisions are made based on some objective information, and this information is a public domain knowledge. So if we read this carefully, this lots of words, but they consider just this situation, like I know that you know, and you know that I know that you know, and so forth. So every other action depends on their beliefs about what each other player does. Like as if a player is a reasonable player and he analyzes the objective information available to both players, then there are obviously ways to find moves which would be preferred by both players. So that's how this decision theory works and decision-making procedures work. Like we analyze our information available, objective data, objective information, and pick the options which suits the both parties. The aim of every game is to win. And here we consider the games, the so-called zero-sum games. This is the kind of games where one party win equals to the other party loss. So basically we describe with the same number the win by one party, and the win for one party means exactly the same amount of loss for the other party. So we can start considering this game with the payoff matrix which we considered before when we considered games with nature. Now we embark on a journey to formalize such games. Let's consider a matrix. This is a matrix. It contains different payoffs. The payoffs, this F1 sub 1 1, F sub 2 1, F sub 3 1, these individual numbers, and they're represented with letters and with some subscripts. They represent individual payoffs, which could be, say, payoff for player A, or at the same time, this is the loss for the player 2. So the matrix organized is as follows. We have different strategies, or we have different options, decision-making options available for two players. Player A have his strategy A sub 1, A1, strategy A2, strategy A3. Player 2 also has 3 strategies available, but that's not the case always. Like both players can have different number of strategies available to them. But at a combination of every strategy, for example, strategy A1 available for player A and strategy B1 available for player B, there is a number at the crossroads between these two strategies. For example, player A plays his strategy A, or picks his option A1. So depending on the moves by his opponent, he can obtain either this payoff or this payoff or this payoff. And this same principle holds for player B. He loses F sub 1 for strategy B1 if the player A plays A1. He loses this amount of something, some resource, if the player A, if he plays strategy B1 and the player A picks his strategy A2, and so forth. Now, which strategy is the best for every of the two players? This matrix is public knowledge. So these numbers, the payoff for one player and losses for the other player, are in public domain. The probabilities of various strategies are not available yet, and there is no information either about which particular strategy the player A has actually taken. So we need to analyze this matrix to find, in some sustainable way, to find an option, a combination of strategies which would which would be advisable for every player to pick. Let's state some limitations. Only one strategy here can be used at a time. Combinations of strategies are not available yet. Again, we talk about games in so-called pure strategies. So pure strategies means that only one strategy can be used at a time. Sometimes both players can use a mixes of strategies. For example, he can randomize between strategy A1 and strategy A2 or strategy A3. So we can introduce either shares of the strategies or probabilities of picking the strategies. So using that situation when a player uses a combination of strategies will be called the game in mixed strategies. Now, let's get back to the payoff matrix. The strategies available to both players together with payoffs are public knowledge. So this matrix is known for both players. And let's assume that player A makes the first move. Now, which strategy player A is to adopt, depending on the strategies available to player B. Since the payoff of the player A depends on the action by the opposing player B, he can maximize only his worst case scenario payoff, or minimum across the column. The minimum across the column. It's like in game with the nature, when the decision maker could have only optimized his worst case scenario payoff. So formally, this means that player A should minimize payoffs across every column, minimize payoffs across the column, find minimum here, then find minimum payoff across this column, minimum payoff across this column, and pick the maximum. Formally speaking, it looks like this. Player A analyzes the payoff matrix by minimizing or finding minimum across the column, every column, and then maximizes or picks the maximum of these three minima. So the this formula just states this obvious approach. So alpha is called the bottom price of the game, and the corresponding strategy is called the maximin strategy. Again, as the formula applies, we just spell it out. Maximin means we find a maximum of several minima, and the corresponding value or payoff will be called the bottom price of the game. On the other hand, player B tries to minimize the player's A payoff, or at the same time minimize his own loss. So the best he can do, again depending on the moves available to player A, he can maximize payoff, he can maximize his losses because the player A plays against player B, and he wants to maximize the losses for the player B. So player B can find only his worst case scenario, and his worst case scenario is maximum losses in every row of this payoff matrix. So he finds maxima across the columns, across the rows of the matrix, and then picks the minimum, minimize this maximum, one of these maxima. The number obtained in this manner will be called the ceiling price of the game. Beta is the ceiling price of the game, and the corresponding strategy is called the minimax strategy. Again, we'll just spell out this formula: min-max, minimax. So when we get to the example, this will become more obvious. But let's get to this example which is not so obvious. Let's think through what this simple game. A businessman, player A, trying to escape the creditor, player B, and he can hide at one of the two places. Point 1, his strategy A sub A1, or point 2, his strategy A2. On the other hand, creditor looks for the businessman, and if he finds his whereabouts, then he gets the sum of 1,500 the businessman owes him. Otherwise, the creditor doesn't get his money. Evidently, the creditor, on the other hand, has two strategies. B1, look for businessman at point 1, or B2, look for businessman at point 2. We get this payoff matrix. A1, A2, B1, B2. So, if the businessman picks the strategy A1, hides at point 1 and the creditor picks his strategy B1, then the businessman loses $1,500. But if the creditor picks the strategy B2, the businessman doesn't lose his money, and the creditor doesn't get his money the businessman owes him. The same goes for the option 2, or the hiding point 2. So there are two situations or two combinations of these pure strategies when the businessman loses his money or creditor gains his money from the businessman. The combination A sub 1 B sub 1, the businessman loses. A sub 2 B sub 2, again businessman loses. But at these two strategies, A sub 1 B sub 2, businessman wins. He doesn't lose his money. And A sub 2 B sub 1, the businessman wins. He doesn't lose his money. So even though this is a very simple game, this is a very good example of, and actually it might look like this payoff matrix and this game doesn't make any sense, because what's the point if these places are available, these points, the hiding places are in public domain, knowledge in public domain, and there are only two places to hide, so it doesn't make any sense. It might look like this, but actually this payoff matrix describes a very interesting situation. In pure strategy, this game has two solutions, but we can also solve this game in so-called mixed strategies, when the player A, the businessman, and the creditor start randomizing their whereabouts. Like when the businessman picks the hiding point at random, either A sub 1 or A sub 2. This makes the creditor also randomizing his strategies. Now this game makes a little bit more sense, right? Because you don't know exactly the whereabouts of the businessman, so you have to pick the seeking place or place to seek him at random. But first, let's consider the solution in pure strategies. We just apply the formula and formal approach. So the businessman or the creditor, actually the businessman, finds the minimum across the column, and it's minus 1500 in the second column. The maximum of these two minima is minus 1500, so this is a solution. This is a solution. Businessman loses 1500, and the creditor gains 1500. On the other hand, the other player B, can adopt any of the two strategies available to him. Again, he applies his maximum approach, his maximum solution. He finds maximum across the rows. Finds the maxima across the rows. Maximum in this row is 0. Obviously, maximum in this row is 0. The minimum of these two maxima is 0. So again, player B can adopt any of the two strategies available to him. So in pure strategies, this game, a solution to this game might not look like having much sense or making much sense. But in mixed strategies, It makes more sense. Let's introduce some notation here. Usually the ceiling price of the game is higher than the bottom one. So alpha is less than beta. Beta is the ceiling price, alpha is the bottom price. However, sometimes these two prices are equal to each other. Sometimes bottom price is equal to the ceiling price. So then we call them just price of the game and denote it as V capital. In this situation, when bottom price equals the ceiling price, the payoff matrix has the so-called saddle point. This means that there is an element in the payoff matrix which is minimal in its row and maximal in its column, all at the same time. All at the same time. Now we'll see it at an example. The saddle point has the following meaning. If one player takes the strategy corresponding to the saddle point, then the other cannot play better than when also adopting the strategy that corresponds to the saddle point. And we assume that every player is a rational player. So he behaves rationally. He analyzes the data, objective information available to him, and picks his best choice. This also means that minimax and maximin strategies that correspond to the price of the game are the optimal ones. So these two minimax and maximin strategies are optimal ones, and their combination is the solution to the matrix game at hand. Let's consider this simple example. Player A obtains maximal guaranteed payoff or win, which doesn't depend on the choice of strategy by player B. And player B obtains minimal guaranteed loss that doesn't depend on the choice of strategy by player A. Now this solution is found by finding the so-called saddle point. Saddle point. Again, how do we do this? We find minimax strategy for one player, for player A, and we find maximin strategy for another player. So, for example, we find minima across the rows. We analyze the first row. Strategies available. Strategy A1 available to player A. And we analyze these payoffs across the choices or options available to player B, who plays against player A. So obviously, if the player A picks this strategy to obtain this payoff of 7, he wants to, for example, player A wants to obtain the maximize this payoff, or shoots for this payoff of 7, then the player B can negate this by picking his strategy B1. So instead of obtaining this payoff of 7, player A gets the payoff of 2. So this is his minimum payoff in this situation, which is his worst case scenario in this particular situation. Now he analyzes his next strategy. Again, he might have shot for this payoff of 8, but the player B can negate this, can beat this by playing strategy B2. So instead of getting 8, player A gets only 6 if he picks this particular strategy. So the minimum here is 6. Minimum here is 6. The same applies to the third option. Player A, the minimum here is 1. Now, the maximum of these three minima is 6. So obviously the maximum guaranteed payoff for the player A is 6, which is this one. At the same time, player B can minimize his maximum losses. And again, it turns out that it equals to 6. So the maximum in every column, here it's 7, this one is 7, here it's 6, here it's 8. So obviously the minimum of this maxima is 7, or 6. Minimum of this maxima is 6. So 6 at the same time, this payoff of 6 is at the same time, it corresponds to the maximin strategy and minimax strategy. So this means that this particular point is the saddle point. So the price of the game is 6. The price of the game is 6. It means one player, for example player A, wins 6 of something, and player B loses 6 of something, for example $6. And there is no price difference that could be split among the players. So it's single solution, single combination of strategies, which brings us to the solution of this particular matrix game. However, sometimes there are situations where there are no saddle points, and the bottom price is less than the ceiling price. The bottom price is less than the ceiling price. Then there is a price difference, which can be taken by one of the players. Who takes it? We'll consider this in the next video. Thank you for your attention, and until next time.